The Open Compute Project is a vibrant community that spans the data center infrastructure worldwide. Though not a standards body, the OCP community forges new technology norms, fostering an ecosystem where industry players collaborate in a safe framework, shaping a versatile and diverse supply chain. From startups to hyperscalers, as well as research, academia, and investors, the OCP community is able to reduce procurement time, research efforts, expenses, development time, and even legal complexity for your projects. Participating in the OCP community gives you access to the latest technologies and talent, the chance to improve your skills, and to drive impact in critical areas like energy efficiency, cooling, and sustainability. Join one of the many project work streams to help solve challenges and pioneer solutions, or serve as a volunteer leader to help steer the community towards the industry's ever-increasing challenges. If you're seeking cutting-edge solutions, explore our marketplace or the library of specifications and other contributions, and embrace OCP solutions in your next endeavor, or make OCP specifications part of your next RFP. Check out the latest solutions at an OCP Experience Center, or partner with any of our OCP-recognized facilities or OCP solution providers. Contribute specifications, design files, reference architectures, or software to help solve the industry's greatest challenges, building trust in you and your brand. Connect at OCP events through attendance and sponsorship, and embrace OCP's inclusive, open spirit, because together, we're stronger, faster, and better.
Please welcome Microsoft's Vice President, Cloud AI and Advanced Systems and Open Compute Project's Board Chair, Zaid Kahn.
Wow, it's so awesome to see everyone. I can't see the back anymore. So great to see everybody. It's amazing. Wonderful to be here and seeing everyone again. Familiar faces, and also people for the first time. Welcome. A lot has changed since last year's Global Summit. Late last year, there has been a tectonic shift in the industry. This tectonic shift is the era of AI. It is not a trend, but a major shift in the way technology is going forward to impact our lives. Collaboration has never been more important to solve common industry challenges. For the last 10 years, the OCP is the place for technologists to come together in an open and safe environment to collaborate, and will continue to do so moving forward with future challenges that we are going to experience going forward. One of the challenges that is upon us this year is navigating this shift towards AI and the infrastructure challenges and opportunities. While we have had several waves of AI technology impacting society, this wave is really different. We don't know if this is big as the PC revolution, or the birth of the internet, or the mobile revolution, or perhaps AI is bigger than all of those things combined. The jury is still out. AI can now be used by an average consumer without really deep knowledge about data science and machine learning and the complex mathematical models that the early days, folks were doing. This uptake for AI to assist humans in the workplace is expected to be really widespread. This is driving tremendous round of investments in IT infrastructure and data center build-outs in the very near future. We have seen the recent 5-year data center CapEx spend forecasts have taken significant upward revisions. Most importantly, AI workloads have many new requirements driving new computational infrastructure and architectures. Now, I would like to turn things over to George to tell us more about AI, OCP progress, and this year's Global Summit. Thank you.
Thank you very much. Good morning. Welcome. It is always exciting and empowering, and also, very humbling to be here year over year on this stage with you all. This year, our summit theme, we thought about it a lot, and we made it as scaling innovation through collaboration. And this really fits into our core competency and our brand. And this is where all of you come together to collaborate to build your business and your supply chain. So we're very happy to see you are here. Before I move on, I would like to give a kind of a status update on this summit. So this year's summit is sold out. This is the biggest summit ever that we have, done in our, thank you, in our, 10, 11 years of OCP's existence. Our sponsorship has been incredibly strong, and also our membership has been strong. The participation today, we have more than 4,300 attendees, registered attendees. Thank you. Thank you for being here. And with this, I would like to take a moment to really thank our sponsors, thank our community, our members, our volunteers, and you all for attending. But most importantly, also my team, my very small team, and our event coordination partner, FNTech, for making these events very successful. Thank you all, really, for being here. So let me delve into now the state of OCP. We are growing, and I'll humbly say that it's been an incredible journey of growth. Our membership is growing, and what we have done this year, we have created another tier. We called it Startup Membership Tier, and also a startup program for helping startups. And I'm really very flattered to say that we have 11 of them already joined us. They're really using OCP platform, the collaboration, to amplify their designs, to amplify their value proposition, and make a business for themselves and supply chain. So come join us. And we have a very strong pipeline of all startups worldwide wanting to join. This is great news, and I just want to make sure I highlight it. Second, collaboration. As we said, we cannot do this without you. We cannot do this without collaboration. And it's been very strong with our alliances. And specifically with our existing alliances with Linux Foundation for hardware and software co-design, and for JEDEC for all this chiplet economy, for all the silicon movement that we have seen. And with this, because of this whole growth, our contributions from you, contributions to OCP, to the community, has been invaluable, and it's been growing. Really appreciate it, and thank you very much. So again, scaling innovation through collaboration. Second, I would like to also let you know that the foundation team has been working very hard to make this impactful, very impactful summit and very influential summit. With this, we have extended and gone through complementing our content, and we have now, we have about 3 important tracks: AI, optics, and quantum technology. Even though quantum technology is in infancy, we want to get ahead of it as seeding the market. So please make a moment and make sure you attend this events. There's going to be very informative. I'm also happy to let you know that after COVID, we have seen this influx of membership coming worldwide. Really incredible, and we love it. And here is to let you know that there are 3 bigger programs here to make us very impactful and expand our footprint worldwide. First one is our emerging market and also our marketplace. If you're not using our marketplace to showcase your solutions, you should. We get about 8,000 or plus hits per month. The next is our service providers and the solution providers. We have grown to have 50 of them worldwide. And of course, last but not least, is the OCP Ready program for creating OCP facilities that hyperscalers, expand to make sure that they are ready. So with Google's help, Meta, Microsoft, we're making that a reality. Now, let me delve into AI inside OCP or at OCP. From the conception of OCP 10, 11 years ago, we never wavered from designing, specifying, deploying large-scale computational infrastructure for HPC, for high-performance computing. And with the evolution of AI, especially LLM, large language use case model, we see the natural progression inside OCP. So it's not like we're forklift this. This is really natural for us. And for that, naturally, OCP is going to allow the foundation, the platform for all of you to collaborate, to come in, and make sure that we see the promise of AI through our collaboration collectively. To make it more impactful and also to make it more, let's say, tailored and more practical, we already started pushing the envelope of OCP. And one thing that we have done is sustainable large-scale computational infrastructure really tuned for AI. Here we have 4 areas, 4 vectors that we are pushing. First one is, of course, specialized computation with chiplets. The second one is optical networking. This is for low latency, low power, high bandwidth, the cooling, the aspects of whole cooling, with immersion cooling, with liquid cooling, and the last, of course, with memory, and especially with CXL, memory appliances. Now, we're not done yet, because this is the foundationally how practical we can move. We are going to put the system envelope on top of it with our board members, the hyperscalers, to really help us move forward, like I said, and make the promise of AI happen. I'm also happy to report that next year, beginning of next year, we are going to form an advisory council from you all, because we're growing. This advisory council will advise our board, myself, the CEO, but this is also trying to make us more inclusive and try to bring the talent into OCP to make sure that we serve you better. And we're going to just be in tune and stay tuned. Next couple of months, you will get more information about how the application, the process, and we're going to make it open and transparent. With this, I would like to also now talk about alliances, what we're trying to do to build AI clusters, and also to highlight what are the initiatives inside OCP and what alliances we're building around this. With that, I would like to welcome on the stage Cliff Grossner, our Chief Innovation Officer, to tell you more about it.
Well, welcome everyone. I'm really excited to be here. It's going to be a great few days on the event. And I've got a lot of exciting news to share with you. First thing is a new dimension for OCP, a new emerging market program, OCP Safe. OCP Safe is designed to reduce cost overhead and redundancy of device security audits, while at the same time improving the trustworthiness of devices across all data center IT infrastructure. Like many things at the OCP, OCP Safe starts with the OCP community, developing a standardized device-specific audit checklist and criteria for selecting third-party device auditors. Bringing standardizations to device firmware security validation, helping data center operators maintain a consistent security policy. With each device release or firmware upgrade, a third-party auditor will use the standardized checklist created by the OCP community to validate the device firmware security posture and produce a report. That report can be available at the OCP marketplace for all to view. The good news is OCP Safe is already up and running. We have participation from device vendors AMD and SK Hynix. Intel's also working with us. And we already have security auditors signed up and ready to go, IO Active, NCC, and Atreides. Another piece of news that I want to share with everyone, shifting gears a little bit, OCP's technology incubator is graduating a second work stream, demonstrating continued success, taking technology from inception to productization ready. More specifically, Cloud Services Model, a FTI work stream, moves over under OCP's hardware management project, ready to deliver approved OCP contributions because it has now been matured over 3 years. And at the same time, it's been responsible for strengthening several of our external alliances. You may recall earlier this year, we launched OCP Startup Membership Tier that George talked about and program. Well, I'm really pleased to share with you the first wave of OCP startups, and no surprise, when you look at the 4 dimensions of problem areas that George highlighted earlier for AI, they actually cover off all of those problem areas, bringing new blood and ideas into the OCP community. I have one more announcement to share with you. Again, you may recall last January, OCP announced an alliance with JEDEC to deliver a worldwide standard for electronically describing chiplets, to be achieved by merging OCP's ODSA CDXML into JEDEC's JEP30 part model guidelines. Well, the good news, that work is now complete, and CDXML is part of JEDEC's global standard. So with that, I wish you all a great few days, and I'd like to pass things back to George to tell us a little bit about the upcoming week at Summit.
Thank you, Cliff. So without further ado, we have a lot of packed schedule here. So I want to mention a couple of things about the summit so that there are new in the summit. So we're breaking the breakout sessions now. We're doing it for 2 days to give you more ample time. And also, this is the first time ever at the FTS, the Future Technology Symposium, we're going to show real demos, actual demos, okay? So just that you know. Next, I just want to make sure we give a shout out to our co-located partners who are driving this summit to do bigger ever. Here you can see on the stage what they are presenting. Again, I recommend and urge you to go see it based on your need for your business development and also your supply chain. Another shout out that I need to mention that we're having a special event for Samsung is doing a Samsung Memory Day on Friday. See us and make sure that it's going to be on this stage, on this platform, and hopefully you can attend as well. For AI, as we discussed, next 3 days is going to be packed. For a lot of discussions about AI at the Global Summit. Again, I'll leave it up to you. These are in your schedules. If you like to attend, and make sure that you are there. And one day we're going to also talk about the quantum technology. Now, and last is we're going to invite on this stage our esteemed colleagues from the industry to give their keynotes about why they use OCP and what are they doing in their industries, in their companies to really accelerate their businesses and also how to collaborate. We put them into 2 categories or 2 groups. First, we call them the cloud technologies or the technology providers, and of course, adopters, who are the hyperscalers, and of course, all of them are members of our board. So with that in mind, I would like to say thank you again for all of you, for our sponsors, for being here. Thank you for attending the summit. Enjoy it. It's impactful. It is going to give you a lot of information. Go out there and harvest it for your own need. And with that, I would like to bring on the stage Zane from Intel to give his first keynote. Thank you very much. Enjoy the summit.
Good morning, everyone. It's awesome to be here to help kick off OCP. What could be more top of mind today than AI? AI is exploding, creating new system design challenges for us, and I wanted to dive into that today. But first, I wanted to just highlight the collaboration between Intel and OCP partner companies. We were one of the founders of OCP. We've been here since the beginning. We've made endless contributions of technology, specifications, led work streams, contributed to work streams. This is a community that can solve important and difficult problems. When I look at this big audience here, I just see the possibilities, and that's what we're here to do. And in fact, I want to just kind of dive right in to what I think is the most important problem facing us today in this AI explosion, and that is the problem of power consumption. So AI models are growing at 10x per year, driving huge infrastructure builds that consume megawatts of power, and we really have to address it. From a carbon footprint and from a sustainability point of view, there's so much that we need to do. Sustainability was probably the biggest topic at last year's show, and with this AI explosion, the urgency is only amplified. I have sort of three thoughts on this topic I thought I would share today. And the first is how modularity and modular system design, which has made big gains, and we're going to talk about that in a second, how we drive more efficient compute and how we extend that grand collaboration between hardware and software to drive really big gains. You know, the gains of the last decade driven by things like virtualization and now acceleration, not just of AI workloads, but all workloads, are creating new opportunities for us to really move the needle on power consumption. So let's dive right in. Modularity has been a topic at OCP, and we've really built out together an amazing array of specifications of interoperable building blocks that allow us to reuse and really drive carbon footprint, embodied carbon of our designs down. The foundational specifications are things like DCMHS, DCSCM, and OCP NICs. And now you can see, new specifications coming online, 3 new specifications this year, building out this portfolio. We also have new companies joining the DCMHS family with Ampere, Jabil, and now NVIDIA. I think the task forward is clear. We need to take what is now, I think, a robust ecosystem for standard cloud deployments and really expand it upwards for AI, as well as into smaller form factors in the edge. And we've really invested at Intel in this, and in our forthcoming platform for our Granite Rapids and Sierra Forest platforms, we've built a whole ecosystem based on these OCP standards. And you can see the flagship partners that we have here, companies like Quanta, Wistron, ASUS, Inventec. Supermicro has been a key partner for us with an OAM solution for our Gaudi 2 accelerators. We really believe in this vision, and we are working hard to make it a reality. And in fact, I wanted to show off some of these solutions. You can see here these 2 Quanta boards. The full systems are on the show floor. You can see them. This one in particular, this is a 12-channel motherboard supporting up to DDR-8800 speeds with our Monument Creek technology, supporting forthcoming Granite Rapids and Sierra Forest CPUs, up to 576 cores. This is the little brother, the 2 DIMM per channel, 8-channel solution for that. And so these are fully DCMHS compliant and support that whole ecosystem. But we're not done with standard 2-socket servers. We really need to build out this ecosystem around the edge. And so we have been partnering with Foxconn Industrial Internet for some years to bring to market modular solutions in smaller form factors. And so this is a great example here from Foxconn Industrial. This is a Sapphire Rapids, a 4th generation Xeon with a vRAN boost technology. This is for the 5G vRAN market. You can see how compact this form factor is. I think this is an excellent example of where we can go with next generation standards. Okay, so modularity can get you that 30% reduction in embodied carbon, but what about actual energy efficiency of the computers themselves? And so that has to be a key focus. And a couple of items here that I'm just super excited about. I have something to show you. This is our forthcoming Sierra Forest CPU. So this is a Xeon processor based on Intel 3 technology with 288 cores. 288 cores. This will deliver 2.4x performance per watt improvements and a 2.5x better rack density. A rack with Sierra Forest 288 core CPUs could have as many as 11,000 cores. So this is a kind of dense infrastructure just unimaginable a few years ago, and I think it's essential to achieving the kind of perf per watt and the kind of infrastructure that we need to make room for AI. But that's not all. I think we have to look also at liquid cooling. And liquid cooling, I think, is a really exciting area. It's come a long way. I think we have to recognize that it's going to be pervasive. Liquid cooling is important for 3 reasons, and probably most of you know this. Number one, it allows us to save 30% power at a data center level right off the top. We spend so much power in fans and in cooling systems, and liquid cooling allows us to just sidestep that. Second is water consumption. The water consumption of data centers with evaporative water cooling is extreme and impacts communities. And many of us are working hard on water conservation projects. By moving to liquid cooling, we can just sidestep the issue entirely. And then finally, silicon's going to push us there anyway. It's only the nature of Moore's law and the roadmaps that you see for GPUs, switches, even CPUs that are going to push us into these very high power domains. You're going to be encountering 1 kilowatt plus silicon that's just going to demand liquid cooling. So it's time that we get started building the standards and the ecosystem to support wide adoption, whether that's direct to chip cold plate style liquid cooling, the more traditional style, or fully immersion solutions which achieve the best energy efficiency possible. And the immersion ecosystem in particular has made a lot of gains in the last year. A year ago, we released a spec through OCP for an immersion fluid standard. And the response to that has been tremendous. There are 16 fluids that have been targeted towards this specification. We just announced a partnership with Shell just last month on qualifying their fluid in the Intel Advanced Data Center Development Lab. These hydrocarbon-based fluids can deliver high performance and a more sustainable solution. So the immersion ecosystem moving very rapidly, and I think becomes a really key alternative for high energy efficiency deployments. Okay, let's talk a little bit about hardware-aware software and what we can do with the hardware and software collaboration. I think this is the most impactful area if we want to have a really significant impact on power consumption, if we really want to make room for this big expansion of AI that we're all working towards and dreaming about. So, it's no secret that model sizes have been expanding 10x per year. And I think for the largest frontier type models, that's going to continue. And certainly there is a place for that. But something that's received a great deal of attention in the last year is the rise of what we at Intel call expert models. Some people call them nimble models. It's when we take a smaller model framework, like a good example would be the Llama 2 model from Meta. And these models are much smaller, but when we fine-tune them on data that's specific to the application domain, we get an excellent user experience. But we get it with a vastly smaller model, which means vastly smaller compute infrastructure. So consider for a second like a 275 billion parameter GPT-3 model compared to a Llama 7B model, that's 25 times smaller. And while the fine-tuned model doesn't have the general purpose capabilities, for a specific application, you can get an excellent result. We're using this in my own department at Intel to build out a customer service capability based on our technology and our data. So this is a really powerful technique. And I have a little demo to show you. So this is based on our forthcoming 5th gen Intel Xeon processor. This is going to launch in December. It's compatible with our prior 4th gen platform. And so what we have here, we have the same chip on both sides, but on the left, you see a standard AVX512 acceleration. Both sides are accelerated, but the AVX512 acceleration on the left, and then our latest AMX accelerator on the right. And this is a bit supercharged with the DDR5 5600 megatransfers per second memories that the new platform supports. And so you can see it's a little clunky on the left. You're getting a much better user experience on the right. And the thing to think about here is that this is a good user experience when trained on the domain-specific data, but this is running on a standard server. This is a 2-socket server. It's a 32-core CPU. It's not It's not some super expensive, power-hungry infrastructure. It can be deployed today. It's based on standard software frameworks that have been well-enabled for years. And so performance up by more than 1.6, and the energy efficiency is a 2x improvement with half the carbon footprint of even just the recent legacy acceleration. So by investing in AI solutions in the CPU, we've really made AI on standard servers very practical when fine-tuned with that data. And so just think about the huge difference in power consumption this can make. And I think it's just a key message for all of us as we're deploying AI services. Find the right model for your application. Don't use a trillion element model on an application where a 7 billion element model can do. And we need to keep investing in a full range of AI solutions that hit these different power performance points so we can really optimize the power infrastructure that we use. Okay. Just kind of wrapping up, we need to attack the problem at all levels of the data center. And we can make substantial progress right now. None of the ideas I've pointed to here are long-term new technologies, no real fundamental breakthroughs required. What's really required is cooperation. And so data center level efficiencies, 30% opportunity with liquid cooling. How do we make that more practical? How do we engage more vendors? How do we build better standards to drive adoption, whether that's direct to chip or immersion? Embodied carbon in our server designs. How can we accelerate the move to modular computing? How can we accelerate the circularity and reuse that becomes possible with modular solutions? And then finally, how can we get hardware and software to collaborate better? How can we find solutions with smaller models that don't require so much infrastructure and don't burn so much power? Intel continues to invest in the CPUs to make AI run extremely well on our CPUs so that it becomes a practical application on a standard server. And we're going to continue to do that. The opportunities in front of us are significant, and I hope there's going to be tons of discussion at this conference, not just on these ideas, but other ideas, because I think in this room we have the power to drive very, very significant change, and significant change is certainly needed. So let's go attack it. Let's have a great show. I look forward to interacting with as many of you as possible here on the floor and the rest of the event. So thank you very much.
Please welcome Samsung's Corporate Vice President, JongGyu Park.
Who knows what the future will bring? For many of us, future brings uncertainty. At Samsung Electronics, we see our role as providing a level of certainty for the future. And we believe we've got a track record that shows we are up to the task. My name is JongGyu Park, Vice President of Samsung Memory. Today, I will tell you about the challenges and our strategy. As you know, Samsung has continuously invested in the open source technology, especially the OCP. But first, let me briefly recap the history, our effort in open source. We are convinced that the open technology ecosystem is a crucial resource for solving problems and pursuing innovation. We started developing open technology from 2015, and then started actively participating in the OCP in 2019. This was Samsung's adoption case. Of those 4 years, we focused on building understanding and consensus on open source technology. Then came growth phase from 2020 to 2022. We formed a dedicated organization and contributed to the ecosystem's development. Our fruitful collaboration with OCP's community led to achievements like the Poseidon reference system, mass production of OCP-inspired SSDs, and leadership in the FTI and sustainability. This progress has brought great pride and responsibility among OCP members. Now, we are in 2023, a pivotal moment for Samsung. Through our ecosystem, all the achievements and experience are openly shared with our customers and partners. The innovation and value generated from this cycle will benefit all of us here. We've dubbed this the diffusion phase. Samsung has established 3 important strategies for open innovation. The first, building on an open platform for collaboration. In line with our effort to build an open platform for collaboration, we opened Korea's first OCP Experience Center back in July. It stands at the heart of the Samsung in Korea. George, CEO of the OCP, was kind enough to be there with staff members at the opening ceremony. What an honor. Thank you. The Experience Center is not a place just to experience the Samsung's product and technologies. It will also be a platform where partners, OCP members, and scholars can gather and have honest discussion and find a solution together. As for second strategy, founding the APEC community energized global collaboration, adding a big piece of puzzle in Asian region. To start, the very first OCP APEC Tech Day was held in Korea on July 4th this year. We see great potential as we look forward to connecting American and European communities with the leadership of the OCP. We aim to discover innovative technologies that are specific to the APEC region, especially on semiconductor manufacturers and system and component makers and data centers. Our vision is to leverage the region's advantage to bolster the open innovation ecosystem, serving as a genuine hub in the globe. And lastly, value chain collaboration for sustainability. We are working to ensure sustainability across our industrial supply chain. The OCP Sustainability Project will play an important role in this collaboration. We pledged our participation in the 2022 initiative and are getting ready for the future. Samsung has built a solid technological foundation through our deep understanding and diverse participation in open collaboration. And we aim to work with you to overcome present and future challenges. Here are challenges. Data-driven technologies are undoubtedly experiencing rapid growth. Data requirements for large-scale language processing applications are increasing exponentially. The growth of AI is in stark contrast to memory capacity, which merely doubles every year. This phenomenon has created a huge gap between data processing capability and physical capacity. It results in inefficiencies in the data center and new challenges for the memory industry, namely bandwidth, capacity, latency, and power consumption. But it doesn't end there. The increasing amount of power required to process data is putting a huge strain on the environment. By 2030, data centers are expected to consume 15.6 times as much power as they did 2020. Combined with the climate crisis, this creates the greatest challenge facing sustainable technology development. So, what is Samsung doing? As a leader in memory industry, Samsung is striving to develop total solution across the entire vertical memory. Many of you are familiar with the HBM, DDR memory, and CXL devices. And here, we have PBSSD. The petabyte scale SSD is a fruitful, futuristic solution designed to respond to challenges the memory faces. In the AI era, the data centers themselves will act like a computer, and a storage system acts as a single big SSD. This is what PBSSD is for. It exemplifies the vision of Samsung, improving data center operation with ultra-high density, high performance, and high efficiency storage and power management. The PBSSD combines Samsung's cutting-edge VNAND and device technology and enhances system density as approximately 30%. With specialized power management, it uses about 20% less power. Ultimately, the PBSSD will help to improve the TCO in data centers and alleviate environmental impact. We are also devoting ourselves to researching innovation, packaging technologies. I would like to invite Vincent, the head of the DSRA-AVP, to introduce Samsung's packaging strategies. Everyone, please give Vincent a warm welcome.
Thank you, JongGyu. Hi, my name is Vincent. I'm leading the advanced packaging team in US. I will explain how we can improve the memory bandwidth, latency, and the energy efficiency with the advanced packaging. In packaging die design, so performance and the power bandwidth costs are driving the die package design to 3D. In 3D, also another trend is the design granule is getting smaller and smaller. So in mobile design, the package devices are stacked on top of each other. In HPC, we plan to integrate the memory dies on top of the logic die, which is the die level. In heterogeneous integration, a die will be split and merged with advanced packaging with a different silicon node, which is the block or chiplet level. It may go down to IP level in the future. The advanced packages provide bigger packages and the more mobile connections. So in that sense, and the advanced package will bring better bandwidth, capacity, latency, and the lower power consumption to the memories. So currently, the AI HP machines are using 2.5D packaging based on the silicon interposers. So in the future, we expect the 2.5D packaging will evolve to 3D packaging for more memory bandwidth and energy efficiency. So the 3D memory would provide a lower power consumption by 40% and a lower latency by 10% compared to the 2.5D packagings. But we need to solve thermal design issues in 3D packaging. In 3D packaging, there are two types of packaging technologies. One is a microbump using thermal compression bonding, and the other is bumpless using hybrid copper bonding. The microbump packaging is already in mass production and has been used in HBM since 2016. However, bumpless packagings provide a finer pitch than the microbump, so the more connections are possible. So for this reason, bumpless packaging could increase bandwidth by 40 to 115 times, while also having a shorter distance, lower power consumption, and being also lead-free. And that's not all. It also provides better thermal performance and a 30% higher die powers. So our next step is a chiplet, and the tiny chips that can be as small as a grain of sand. In heterogeneous integration, Samsung is a strong supporter for open chiplet economy. our advanced packaging portfolio includes silicon interposer packagings and the cost-effective silicon bridge packages. In silicon interposer packagings, we support 4 times HBM size, 8 times HBM size, 12 times HBM size. For widespread use of advanced packaging, we are developing cost-effective packaging solutions. So iCube-E is that the one example. iCube-E use a panel-level interposer packaging integrating silicon bridges. Compared to the silicon interposers, the packaging cost can go down by 22%. It can support the bigger package size than the 4 times reticles with a similar signal and the power integrated performance. In order to overcome the memory challenges, we will work together with the companies in OCP. We will collaborate with the design, IP, EDP, OSAT companies within open ecosystem. We will deliver advanced packaging platforms to promote open chiplet economy. We will support CDXML, D2D protocols, and the chiplet development. Thank you very much. I'll pass it back to JongGyu.
Thank you, Vincent. Today, we will explore Samsung's broad strategy to drive open innovation and collaboration. The path ahead is exceptionally clear. We will for sure enhance the collaboration with various stakeholders across the company and sector boundaries. Together, we can discover the essential technologies and pioneer a sustainable future. Please explore the full Samsung memory product lineup at our booth. You can see the PBSSD and ultra-high capacity 256 terabyte SSD and more firsthand. Also, a quick and important reminder. We are here at the OSP Global Summit this Friday. Here at SJCC, you will witness more of Samsung's leadership in memory technology on Samsung Tech Day. I hope to see you then. Thank you.
Please welcome Marvell's Executive Vice President, Optical, Nguyen.
My name is Nguyen. I'm Executive Vice President and General Manager of Marvell Optical Group. Marvell is a leader in data center infrastructure for cloud data center, 5G, enterprise, and automotive. We have been a member of OCP for about 10 years. Our work with OCP spans the whole gambit of optics, connectivity, computing, storage, and security. And for me, I've been working in optics for the past 20-some years. Prior to Marvell, I was co-founder of Inphi. And Marvell and Inphi has been credited for leading the transition of data transmission from NRZ to PAM, and also to transition from the telecom transport big boxes to a pluggable WDM optics that connects data center to data centers. Super excited to be here to talk to you, to all of you, and share with you how optics has enabled AI and the challenges that optics will need to do in the future to support AI. So let's begin. Ten years from now, when we look back, I think most of you will agree with me that 2023 is the new beginning of AI. The world will be very different 10 years from now. Just in the last few months alone, so much that has happened. And let's take a look at Well, that's a lot, isn't it? It's hard to believe that all these things just happened just in the last 6 months. So the implication is, what will it change the data center for tomorrow? One thing we know for sure, data centers have to be larger and consume more power. A typical data center today consumes about 32 megawatts of power. The data center of tomorrow, in fact, they're being built today, will consume 1 gigawatts. And 1 gigawatts is the output power of, say, a typical nuclear power plant, and can power 100,000 homes in a developed society. It's humongous. Furthermore, a campus or region will need to consume not only gigawatt, but multi-gigawatts. As data centers getting larger and further apart, you need more and more optics. High-speed optics. High-speed optics is what enables the scale-out of data centers. On your left is what we call the scale-up model. In a scale-up model, memory, GPU are being added to an AI server. And all of the added memory will work with the AI server as a single GPU. Today, that limit is about, say, a few hundred GPU. And the AI computer being connected this way can deliver up to about 1 exaflop, which is a humongous amount of computing power. However, that is actually pale in comparison to the scale-out model, which is on your right. In the scale-out model, AI servers are being added in parallel, one by one, via high-capacity switches, high bandwidth network optics. And in theory, you can scale to 10,000 GPU or limitless, as long as you have enough space, enough power, enough bandwidth, and low enough latency. But the reality is not. Bandwidth is limited. Switching is limited. So today, the largest AI cluster that can be built with the current switches and optics is roughly in the order of tens of thousands of GPU. And the performance of these clusters in the future can approach hundreds of exaflops, which is humongous. Because of that, large AI clusters span hundreds of meters, thousands of meters, and data need to traverse this network in a single iteration. We estimate that distance in a single iteration can be as much as 10 kilometers in a single iteration. A large training model, a workload, may take hundreds of thousands of iterations. So data need to traverse as much as 10 million miles. I know many of you in this room are frequent flyers. I am. Most of us don't fly 10 million miles over our lifetime. But you can see the problem. Now, because of that, the network is now the new bottleneck. For AI to be able to scale up to hundreds of exaflops, you need high-speed optics. You need bandwidth, you need low latency, and you need high-capacity switches. The demand for bandwidth for optics will explode over the next 3 years. Estimate vary from 100% CAGR to whatever the number. We use a somewhat more conservative number, 78% CAGR growth in bandwidth, or 6 times in 3 years. When I share this data with my friends at some of the hyperscale, they told me that, "Lord, you're way conservative. This could even more." So we'll see. So there has always been a race to develop higher speed optics. I remember we were so excited when 40 gigabit got deployed in sometime in 2014. That was 10 years ago. Early this year at OFC, Marvell and our ecosystem partner live demo a 1.6 terabit optical module. 1.6T, that's 40x over the course of 10 years. The industry is also doing a pretty decent job in reducing the power per bit. So over the course of 10 years, the power per bit has been reduced by a factor of 10, roughly, not quite. But that's not enough. As you can see the math, 40x increase in bandwidth, 10x reduction in power per bit. Net is that the power of optic module has increased every single generation in absolute term. And that creates a problem. One of the other metrics that we often use is what is the networking power as a percentage of computing power. For traditional cloud server, it was in the low single-digit percentage, not a problem, not a problem. For AI, the equation changes. For, say, a 1K GPU clusters, the networking power is about 5% of the compute power. And I'm talking about bare-bone networking power, only including the power in the switches, in the optics, without any cooling or anything, or any support structure. It's 5% today already. But as you grow to a cluster to, say, 4K GPU, that percentage has risen from 5% to about 12%. 12% is significant, and I'll show you why. Recently, Meta announced the plan to build a 32K GPU clusters. So I was intrigued. So I was in Scotland for the ECOC conference. We sketched out how to build this 32K GPU clusters. We need at least 3 layers of switches, at least. And even using oversubscription, 7-to-1 at the top layer. The reason for that is because there isn't a switch big enough today. There's nothing to be able to connect 32K GPU together, any-to-any non-blocking. So you have to use oversubscription at the top. And even that, the number of switches is staggering. Over 2,000 switches. And we're not talking about top of rack here anymore. We're talking about, at the spine and the aggregation layer, big switches. 4Ks of server, 70Ks of optics. And these clusters will consume 45 megawatts of power. Just think about it, 45 megawatt of power, more than a typical power in a data center today. And previously, I showed you networking power is 12% of 45 megawatt, and that's a 5.4 megawatts. So clearly, that is a very big number. So we at Marvell, we believe in open ecosystem. From the start of the company, we always work with different organizations to create open standards. We are working with other component vendors, our competitors. We're working with many competitors, actually, and module partners, OEM, hyperscale providers, end users, to build this optics ecosystem. Today, it is a $10 billion open ecosystem, very, very strong, with many vendors who can scale it up to millions of pieces per year. And I have confidence that this ecosystem will be able to scale up to the challenge for AI tomorrow. High bandwidth, low latency, and low power. Personally, I'm going to do everything I can to reduce power of optics, because that's something that I have some control over. We will see less than 10 picojoule per bit in the next few years. So with that, I'd like to conclude my talk. But before I do that, we've been doing a lot of investment to support AI. So my question is, what will AI do for us? I don't know who to ask, so I turned to ChatGPT. I said, what are you going to do for us, humanity? And ChatGPT, you know, very diplomatic. Well, we can't really say anything with precision, but we have a few suggestions we can offer. So please take a look. Better talk to whale. And travel to Mars. Thank you, everybody. I hope you enjoyed the show. And I wish you a great OCP Global Summit. Thank you.
Please welcome AMD's Executive Vice President and General Manager, Data Center Solutions Business Group, Forrest Norrod.
Hey, good morning. It's great to be here with all of you. It's a very large crowd, super impressive. I remember 12 years ago talking at the first OCP meeting back in the Facebook buildings, and my, how the organization has grown since then. And the importance of what you are doing, what we all are doing together, has never been more important. Today I want to talk about how we harness everything that we've done over the last 10 years to meet some of the looming challenges in the data center. And the biggest challenge, of course, is the one that you've heard from multiple people already, the challenge that the AI systems are going to bring to the data center. And so first off, I'm very proud to say that AMD has been a close partner of Open Compute since the beginning, with participation on the Steering and Incubation Committee and across many different subcommittees over the years. And it's been our pleasure to support the development of all of those different technologies and open standards to try to meet the continually evolving and growing challenges of the data center. And we've struggled, quite candidly, over the last 10 years to keep up with the insatiable demand. IT has become part of our lives in so many different ways that's generated enormous demand for IT services and put tremendous pressure on the data centers. And we've struggled to keep up with that to the point where today, about 3% of data center capacity in the world is free and available for new deployments. The rest is already in use. And we're really going to struggle, as you've heard already, to keep up with the growing demands of AI as we start contemplating clusters like Lloyd just mentioned. But AI is coming. The productivity gains we've already seen from so many of the large language model deployments means that it absolutely will become a central part of many cloud and enterprise data centers across the world. But in those data centers, even a modest AI deployment can cause a big problem. A few hundred systems, if you do the math and extrapolate from what Nguyen and others have already said, hundreds of kilowatts, and can break the back of your data center. If it's already anything close to typical utilization, this might force you to build a new data center or secure a lease on long-term capacity with significant financial implications. Well, the solution to that problem is in part to build new data centers, sure, but that's impractical to meet what we think is going to be becoming tsunami of demand for AI. And so what we have to do is we've got to make a big part of the solution today's data centers. And the good news is there's a lot of them. We've got a lot of power. We've got a lot of space in those data centers. But again, the utilization is very, very high. And so to solve the problem, to use this existing asset, We have to continue to drive power efficiency in the data center across every aspect, and we need to drive performance density in the data center as well. We have to solve both sides of the equation. Now, we've made progress on energy efficiency over the last 20 years. If you take a look at, and this chart is for x86 spec power benchmarks, so the leading system, leading x86 system, in this case, this is entirely an Intel line. We've made tremendous progress over the last 20 years in increasing the power efficiency of the fundamental element of compute, the server. In recent years, with the introduction of additional players into the data center, AMD, and of course, some of the ARM entrants, we have some new perspectives on how to drive power efficiency, and luckily, we've made more progress and helped inflect all of the slopes of all of the lines to get steeper so that we can make more progress going forward. But the progress that we've already made is pretty substantial, and it can lead to enormous savings. If you look back at the systems you would need to have to deploy a workload that required, say, 20 million spec-int rate worth of performance, probably in that time frame, that'd be 40 or 50,000 servers. And you look at delivering that same amount of performance today with the leading x86-based servers, we've seen a 4-to-1 reduction in the power required, saving 31 megawatts of power from that deployment with 5-year-old technology to the deployment with the latest technology of today. So we've made a lot of progress on energy efficiency. And on performance density as well, we've made a startling amount of progress if you step back and you look at it over the last 5 years. So again, the top published benchmark for a 2P server back in 2018 was 327 spec-int rate for a 2P server. And today, the top benchmark is 2140. We've also, again, seen some ARM entrants at this point, so this is not just an x86 race of increasing performance density, but we have seen about a 7x improvement in performance density just in the last 5 years. If you put those two factors together, it's pretty clear that the solution for many of the most pressing immediate challenges of where do I put these AI servers is in consolidating the systems that are used for existing workloads and consolidating them with the latest technology. You can drive almost an 80% reduction in the physical space, the physical number of servers required to deliver that level of performance, and you can cut your power consumption to a quarter of what it was used previously. And again, these workloads are not going away, guys. The problem with AI is it's an additive workload that has tremendous value. But that doesn't mean that the existing services, systems of record, transaction processing systems, et cetera, they're not going away either. So we have to find a way to allow the two to live together and for the legacy to give way in terms of embracing efficiency to make room for the new deployments. So, great improvements over the last 5 years. How did we achieve this? Well, I'm a silicon guy, so most of this talk is going to be about silicon aspects, but it goes beyond that. But it does begin, in our opinion, with efficient cores. So if you take a look at a modern core, a Zen 4 core in our latest generation EPYC processors, that's about a little less than 4 square millimeters of silicon area. The competitive core in Intel 7 today is about 10 square millimeters. And by the way, the core from 5 years ago is also about 10 square millimeters. I thought about drawing it on here, but you wouldn't really see much difference. And these cores are very different in area, but they're pretty similar in terms of performance. The AMD EPYC 1 happens to be about 17% faster than the competitor when gauged core to core. So efficiency in the core, stripping out unnecessary crap, and that's been, unnecessary stuff. And that's been a theme of OCP from the beginning. I remember Jonathan Heiliger's first blog was talking about get rid of everything unnecessary that doesn't add value. That's our perspective as well. In the cores, you don't have accelerators in each core for functions that are only used by a small fraction of the workload. You have a clean core, you design it efficiently, you pack them in, and then you use accelerators elsewhere, as I'll talk about in a minute. But it's not just the core, of course, it's every trick in the book. Of course, on the silicon side, process nodes, packaging, et cetera. On the system side, a lot of innovations, particularly around power, cooling, and power delivery. We used to say that Moore's law would solve all problems and would keep driving the density and power efficiency of silicon up. Unfortunately, it really has inflected down. I wouldn't say that Moore's law has ended, but certainly the slope of improvements has inflected down, and we think that this will continue going forward. So to get around that, to be able to continue to drive the performance density and power efficiency, we're having to take alternative methods to get more silicon, more transistors into each chip. Chiplets and advanced packaging have already delivered and will deliver a lot of additional options. From the monolithic silicon days where you could have one chip in a package that really could be no larger than a reticle, and even if you made it close to a reticle, the cost was prohibitive. From that, we moved to multi-chip modules, to chiplets, where you have, in addition to a large number of chips, you're using heterogeneous processes to tune the process to the type of logic or problem that you're trying to solve with that particular chiplet. To now 2D and 3D technologies and full-up 3D stack technologies. We've gone from an era where we can get 700 to 800 square millimeters of silicon into a package to well over 3,000 with what we'll be delivering this year. And if you include the memory that Samsung mentioned as well, over 14,000 square millimeters of silicon in one package, and I see no reason that that's going to stop anytime soon. So that's going to continue, and that has helped a lot with driving that performance density. The other aspects of the system design are also critically important, and here's one area where OCP has really made a difference in driving power efficiency of all of the steps of delivery, of driving efficiency of fans, of driving efficiency of cooling writ large, of embracing liquid cooling and driving that going forward, and that's going to be critically important. I completely agree with Zane on that going forward. Every aspect here is important, as well as just driving the PUE in the data center as well, because that's the multiplicative factor, the power utilization efficiency at the data center infrastructure level. That's a multiplicative factor that makes this whole problem worse or better. If we look forward beyond what we've already done, what's next? I think it's clear from the silicon side that we're going to see, as we proliferate these workloads, we're going to see core and CPU designs that are targeted for different types of workloads. At AMD, we've already introduced a line of general purpose processors and a line optimized for cloud and throughput applications with different cores, with different, at least physical designs on the cores. I think you're going to see that more broadly, and Zane mentioned Intel is pursuing this path as well with their forthcoming Sierra Forest. I think you're going to see more targeted use of accelerators. Now, accelerators are a great weapon because they can provide tremendous improvements in performance and power efficiency for targeted workloads, but you should do it judiciously and where it makes sense. The most obvious and highest profile example of that today, of course, is AI, and GPUs and specialized chips do an outstanding job in providing power efficient and performance dense solutions for those workloads. And then very important, the continued innovation around the system level to provide modular systems with really increasingly liquid cooling is going to be absolutely essential, because the power density of the silicon is going to continue to increase. I think Zane mentioned 1,000 watts in forthcoming chips. I think certainly GPUs are well on their way towards 1,600 or more watts per GPU, and it's hard to see where that stops. So liquid cooling is going to go from a nice to have and an experimentation to absolutely critical for any modern deployment. And so what I want to leave you with is, I do think that putting together the progress that we've already made, that we can face the immediate challenge of getting room in our data centers for AI, but we've got to be in this for the long haul. And so commit to continue to drive power efficiency and performance density across every aspect of the data center. Support open innovation by doing it in concert with one another in forums such as OCP and UEE and others. And the last thought I'd leave you with is we're going to want to make sure that we're tracking how we're doing. And so use open, verifiable benchmarks to track the progress. Demand that of yourselves, demand that of your partners, demand that of your suppliers, so that we can track and understand where we're going. So with that, I want to thank you for your time, and thank you for all the efforts at OCP. Thanks a lot.
Please welcome Broadcom Senior Vice President and General Manager, Core Switching Group, Ram Valega.
Good morning, and welcome to OCP 2023. The title of my presentation is, Paths to Singularity. Now, it's a play on words. For those of you who are, paying attention to the whole AI space, singularity refers to a state where the capability of the machine is equals to the capability of a human mind, or in some cases even transcends it. Now, when you think about can we get there, the compute that we need is far more than you can put on a chip, a chiplet, multiple chiplets connected by an interposer. None of that is sufficient. You're probably talking about tens of thousands of nodes, if not hundreds of thousands of nodes that need to be connected together. And when you connect these things together, there's a network that is needed. And I've said this before last year, and I'll say it again. Network is a computer, and that's what we're going to talk about the course of this next few minutes. But before I get started, I do want to take a minute to thank the OCP community. First, for all of you who are here from all around the world, thank you for attending. Over the last decade or so, Broadcom's made many contributions to the OCP community. Obviously, for us, it's a self-fulfilling need to contribute to the OCP community because we are a chip maker. We don't build systems, and we really rely on the ecosystem around us to be able to build these systems, hardware, software, cooling systems, and so on and so forth. And the only way we are able to succeed is by actually having our products, our specs being available to the OCP community. And we really appreciate the support and the environment that you've provided for us to be able to do what we've been able to do. And coming back to, this network is a computer, right? If you look at Moore's law, I think there's no debate at this point that Moore's law has diminishing returns, or at least probably reached a point where you really don't get any benefit from going to successive process nodes, other than maybe some power reductions. But the cost per transistor is going up. But at the same time, the need for computational capacity is increasing exponentially. So how do you then solve this problem where your chips are not getting any larger, the performance is not substantially increasing, but you need many thousands of these nodes, whether they're compute nodes or accelerator nodes, to be able to perform a job function, right? And to be able to do this, you need a network that connects them together so it forms one single large system. So hence, this whole idea that the network is a computer, it's not new. Sun talked about it almost 20 years ago, and we continue to very strongly believe that the network is a fundamental element of scaling compute. Now, the other thing that we've also postulated last year was the network is the compute, but what is the network? And we said, look, Ethernet is the network. It has been the network for cloud computing in the past. It is the network for ML AI today, and it will be the network for ML AI tomorrow in terms of the scale that is needed, right? And we said this actually last year at the OCP, which was in October 2022, before the world kind of got introduced to this whole concept of ChatGPT that happened in November, December of last year. And then you look at what happened in Ethernet over the course of the last year, right? The one thing on the Ethernet is what we all believe in here, which is Ethernet's based on open standards, a very open ecosystem. It's plug and play, it's interoperable. You have a lot of different players in the Ethernet market. Last year, we talked about how there was 600 million Ethernet ports shipped in a year. When you look at all of this, there's a lot of economics and economies of scale in Ethernet. And to make the point about the economies of scale in Ethernet, there's a few data points I want to highlight. First, Ethernet is 50 years old. Actually, I should probably say it's 50 years young because it seems to be getting better with age. Two is the inventor of Ethernet, Mr. Metcalf, won the prestigious Turing Award for the contributions to the world with what Ethernet is able to provide. But outside of these milestones for Ethernet, just over the last year, if you look at the number of vendors that have actually announced high-performance switches to serve the needs for ML/AI bandwidth is amazing, right? You've got Broadcom that's announced a couple of switches almost about a year ago, followed that by other vendors such as Marvell and Cisco, who most recently introduced their 50 terabit switches. But the beauty of this is more than anything else, those who previously were pushing other technologies such as InfiniBand, they themselves have also come and announced Ethernet switches, specifically focused on ML and AI. And that's a beautiful thing, which is the power of the Ethernet, which is we have multiple different vendors all providing an open, standards-based, high-performance network to be able to scale both for today as well as the needs of tomorrow. On that note, the one thing I do want to bring out is at every one of these OCP sessions, Broadcom, we talk about a brand new switch that is just coming out. We just announced it today. This is called Qumran 3D. It is the world's most powerful single-chip router, and that's the most power-efficient device that you'll find there for about 25 terabits, with the power of the entire chip being less than 700 watts, right? What this does is Ethernet continues to scale with economies that no other technology can provide. Now, you don't have to take my word for it. If you just look at the largest operators in the world, all their ML AI infrastructure is connected over an Ethernet fabric, right? And when I say this, there's questions that come back. This is what I call the second-order derivative question. Somebody will come and say, is this the front-end network? Is the front-end network on Ethernet, but is the back-end on something like InfiniBand? No. This is just one single network. It's Ethernet. The front end, the back end, they all converge into one fabric. It's an Ethernet fabric. We're talking about tens of thousands of AI nodes, if not much larger numbers, all connected over an Ethernet fabric today, right? So make no mistake, Ethernet is deployed at scale at the largest operators in the world, and it will continue to get deployed. Why? Because it's very simple. Because Ethernet has an ecosystem that no other technology has. You have troubleshooting, you have testing equipment, you have monitoring equipment, and you have the ability to be able to remove one vendor's switch and replace it with another vendor's switch, or replace one vendor's NIC with another vendor's NIC, and everything should work together. That is why Ethernet is so ubiquitously deployed today, as well as what we believe is going to go forward. Now, you look at all of this and say it's great. You've got Ethernet today. With technologies such as Rocky over Ethernet, you can scale to tens of thousands of nodes. But what happens as we look ahead? If you look ahead, if you just look at the pace at which these language models are growing. In 2020, ChatGPT-3 had about 175 billion parameters. ChatGPT-4 is supposed to have more than 1 trillion parameters, right? So whether these are large language models or recommendation models, what you see is there is a significant scale of resources which are needed to be able to handle the next generation of these models and the evolution of these models. So when we talk to a lot of these operators who are building on these models today and what they're planning on building going forward, the question that comes back to us is, can we have a network that connects hundreds of thousands of nodes? Okay, now suspend your disbelief for a minute. Can you actually cool these things? Can you put them inside a data center? Can you have enough optics to run them? All the other questions that others have brought up in the meeting on this presentation so far. But I would always say, suspend your disbelief, make sure you do what you can to the best, and somebody else will solve the bottleneck another day. So if you ask the question, how do you scale to 1 million nodes? And that's what's being asked. Can we get there? And I promise you, that is the question that most customers or vendor and partners that we talk to are trying to solve. And so with that as a backdrop, how do you scale to hundreds of thousands or millions of nodes going forward? About a couple of years ago, a group of players in the industry got together with the goal of achieving three things. One, Ethernet has the performance of a supercomputing interconnect. I want to repeat that once again. Ethernet has the performance of a supercomputing interconnect. Two, it needs to be done at scale. When we're talking about scale, it's not tens of thousands or a few hundreds. We're talking about hundreds of thousands, right? Scales of 100,000. Number three, it needs to have the total cost of ownership and the ubiquity of Ethernet. They said, if you establish these three as the goal, knowing what Ethernet's already doing today, which is tens of thousands of compute nodes, but going to 1 million nodes, what needs to happen to Ethernet? So as you look at the names on this list, right, these are companies that know how to do compute. These are companies that know how to do networking. And these are companies that have deployed some of the largest cloud-scale networks in the world and systems in the world. They've come together and said, let's actually figure out what needs to happen on Ethernet to improve Ethernet, not because it's not great today, but because of where it needs to be in 2 to 4 years from now, right? And hence, the Ultra Ethernet Consortium was formed with the singular goal of an Ethernet extremely high performance, extremely high scale, at the best economics that any interconnect can offer in the world. And so when you look at that and say, OK, so give me an example of what they were able to do in this space, specifically, we said, OK, let's focus on RDMA. As you know, RDMA is probably one of the most fundamental technologies that allows for memory transfer from one piece of compute node to another piece of compute node. It was built generally with InfiniBand in mind. And over a period of time, RDMA was evolved to be able to support RDMA over Ethernet, which was called Rocky. And Rocky and RDMA work perfectly fine, and Rocky works fine today for many thousands of compute nodes. But the problem is the following. When RDMA was built 20 years ago, the idea was that they were going to be able to connect one node to another node. And then maybe it went from a dozen node to another dozen nodes. And maybe it went from 100 nodes to 200 nodes. Because most of you will probably remember, not long ago, HPC clusters that an enterprise customer or even a large oil and gas exploration would buy would have 256 nodes, maybe 512 nodes, maybe maximum 1,000 nodes, right? That's what RDMA was built for. But today, if you go and talk to somebody about 1,000 nodes, they'll say that's child's play. Even 10,000 nodes has been there, done that. 100,000 nodes and more than 100,000 nodes are what people are interested in. So then you say, well, what's the problem with RDMA? RDMA wasn't built for that kind of scale. There's a bunch of assumptions that RDMA made in the past. There's no multipathing. That is, I can only take one path from point A to point B, and all the traffic flows on that one path. That means I might have a link that is completely underutilized and another link that is superutilized, right? There's the idea of an in-packet delivery. That is, all the packets in a flow have to be arrived. 2 has to follow 1, 3 has to follow 2, 4 has to follow 3, and so on and so forth. And one of these things, like go back n, what that means is, in an RDMA flow, if I dropped a packet, let's say I dropped a packet 5, but I delivered packet 6, 7, and 8 perfectly fine. Go back n basically means, hey, you dropped packet 5, so I want you to retransmit packet 5, 6, 7, and 8, 9 all over again. That is super inefficient, right? And it was also based on the idea that there was a lossless network that was based on DCQC and not based on TCP/IP, which was very, very much more robust. So what happened was you had a very fragile network. You had to super engineer it. Somebody who sold you the system would probably want to sell you everything from the optics to the cables to the systems and charge you like 10 times more than it should be charged. So there's a whole bunch of things that has served the existing marketplace well, but it's not suited for where the world is going forward. And that's when Ultra Ethernet said, hey, look, let's solve this RDMA problem. Let's call it the Ultra Ethernet Transport. And we do a bunch of things. Everything that I said was bad here is going to be fixed in the future. And that's what they're working on without spending too much time on a line-by-line item, right? Net, the idea is you have a very high-performance network, removing all the inefficiencies of legacy RDMA so that you're able to scale to 100,000 plus nodes in a network that is extremely robust. Because one thing in a supercomputing job that is extremely important is if you drop a packet, and there was actually a paper that Microsoft published, that even 0.1% of packet drops causes an exponential increase in job completion times because you have to go back to the state where the packet was dropped and the whole job has to be run all over again. Super inefficient, right? So the idea is a very robust network that's done at scale, high performance, and open standard space. So That's what the Ultra Ethernet Consortium is doing. The initial founding members, it's now been opened up to a whole bunch of other companies. We have an interest list of over 200 companies that are interested in joining the Ultra Ethernet. So all said and done, what I want to close with is the following. In the world of ML AI, it is not going to be one company that's going to provide the GPUs or one company that's going to provide the interconnect. The only way we're going to be able to scale is to have an ecosystem of many vendors providing accelerators. And the only way such an ecosystem is going to survive is to have an interconnect fabric that is open, based on standards, high performance, the best TCO that you can get, and there's no alternative to Ethernet, either today, in the past, or where we're headed to tomorrow. Thank you very much for your time, and enjoy the rest of your day.
Please welcome Promersion's CEO, Rolf Brink.
So, hello everybody. My name is Rolf Brink. Many of you will know me as the project lead for immersion within cooling environments. And although today is actually a bit of a special day, we come with a bit of a celebration. It's almost to the date 5 years ago that we had our very first public immersion community call. And it's not just for immersion, the whole of cooling environments. About 5 years ago that we kicked off the cooling environment solutions calls. So this OCP work is something that I do voluntarily, just like all the other work stream and project leads that we have, which is a lot of them, and they put up a lot of work. I actually make my living running a consultancy firm, Promersion. And as part of my day-to-day activities, I'm very often, slide behind. I'm very often confronted with some similar questions. Questions like, hey, which cooling technology is going to be the technology that we need to invest in? Or who will be the winner? Which cooling strategy can we use to scale out our next generation chips? And this is something I would like to get into today with all of you. And to do this, I need to take you guys a couple of years back to a time where all the data centers were pretty comparable across the board. IT equipment was pretty homogeneous, similar power trends across different platforms. And it's around 2016, 2017 that data centers started noticing some changes in the way that they could roll out their IT equipment and their server racks. And it's also clearly visible here on this chart. Rack density started increasing around that time. And this is something that has been echoed by previous speakers as well. The cause of this is the actual efficiency of the transistor density. The efficiency increases in transistor densities is actually not going as fast as it used to, right? And that is something that we can also clearly see with the trends of the chip densities over the years. There's a clear inflection point at around 2016 where chips started becoming hotter, started accumulating more heat, consuming more power. Even though the efficiency is still increasing and the core power consumption is going down still, the core counts are still increasing. Right? And especially if we're looking at the new chips that are coming out in the upcoming year, we're talking about the AMD Turin or the Intel Emerald Rapids or the B100 from NVIDIA. These are promising to have a significant impact in our thermal footprint. And this is why a lot of the ecosystem currently is so focused on liquid cooling. As you've heard from all the previous speakers, like Forrest, Zane, and Loy, that you've just heard from Intel and AMD and Marvell. Everybody has to deal with liquid cooling somehow. And there are different approaches to this as well. So if we're looking at the NVIDIA platform, which already came out 2 years ago, that's rated for 10 kilowatts. If we're looking at the next GPUs for next year, we're going up to 1 kilowatt per chip. So that box is going to do 16 kilowatts on the GPUs alone, not even looking at the compute on the rest of the components that are in there. Yeah, so NVIDIA is approaching that with looking at two-phase cold plate solutions for the chips, for the GPUs, and immersion for the rest of the compute components in an enclosed chassis format. Cerebras, not sure how many of you are familiar with the company. They're making this huge wafer-scale chips, nearly 25 kilowatts in one of these chips. They have different challenges. They're approaching that completely differently with a single-phase cold plate approach. Storage systems, even the OCP storage system is now going up to the 2 kilowatts. It's already there. It's not a surprise that a lot of the storage manufacturers are actively looking at immersion, full immersion cooling, to cool these platforms. So that brings me to the different types of cooling that we're dealing with in this industry. We can group these in 3 main categories: door heat exchanger, cold plate, and immersion. And these also happen to reflect the main solution projects within cooling environments. And within these projects, there is a huge variety of technologies being represented. And the nice thing is, all these technologies have their own value adds. They're all unique in many ways. We're talking about indirect, direct, and total liquid cooling solutions, whether we're looking at open bath or enclosed chassis. Every one of these technologies comes at a specific challenge that the industry has experienced in a very unique way. And this is part of that growth of the market, and this is where it's really getting interesting. So we've heard from the previous speakers. We know that the solutions and the technologies out there, these are proven technologies. The industry itself is already growing. What we're seeing now for the liquid cooling industry itself is that this year marks a special milestone. The liquid cooling market, and I'm talking about cold plate and immersion by itself, is topping $1 billion in market value this year. And we're well on track on achieving that as well, right? And this is part of a larger movement in the market. It's driven by all these technologies. And one of the significant pivot points in the market at this point in time is the fact that cold plate as a technology is right now transitioning into commodity, which means that new server designs that are coming out of the factories, coming off the shelf, are now being equipped with cold plate technology, right? As part of the chassis, as part of the solution. And that is an incredibly exciting thing to see because it's, first of all, it starts that momentum for cold plate technology, but it also normalizes the liquid cooling infrastructures within data center facilities. Immersion cooling has a few more challenges to deal with, right? So talking about standardization, material compatibility, the chemistry itself, but also usability. These things are difficult to deal with, but we're well on the way on mitigating these, on addressing these head on. And this is also underlined by the incredible uptake of participation in the immersion project within Open Compute. We're the largest project in Open Compute, and the advancements, the utilization of immersion cooling in the industry is no longer hypothetical. It's just a few years behind on cold plate. So if you compare today with immersion cooling with a few years back with cold plate, we're in pretty much the same boat right now. So what do these forecasts look like, and are these even credible? So we've run a lot of different scenarios for the market, and one of the key takeaways here is that the market growth is not a hypothetical thing. These technologies are a necessity. And that means that the basic scenario that we're looking at has an outlook of reaching a 10 billion market in 2030 with an annual growth rate, a compound annual growth rate of 37%, which is really, really good for any kind of market. But if we're looking at the volatility of this market, most of the scenarios that you can come up with relate to the adoption timeline of certain technologies. And a slight deviation in that, with the adoption timeline of some of these technologies, triggers a completely different model with a 20 billion market figure for 2030 and a growth rate of 52%. Right? So with this in hand, which technology is going to be the winner. Door heat exchangers, seeing that now in all the racks, are they going to be able to provide that precision cooling that we're all looking for with these higher chip densities? Cold plate technology, is it really feasible for every transistor or every semiconductor and every component that warms up on a board to equip it with a cold plate? Is it economically viable? Or immersion then? Single phase, two phase, enclosed chassis, open bath? Is it able to deal with the 2 kilowatt plus chips that we're going to be confronted with in a couple of years from now? Before we can really look into this, we're going to need to look at some other numbers again. Remember that homogeneous environment that we had up to about 2015, 2016, 2017? The world looks a little bit different today. This is an estimation of the amount of servers that are shipped per type of system. And one of the interesting things here is that more than 60% of all the compute that is shipped out from the factories actually relates to cloud platforms and general purpose systems. Now, let me ask you this. Do cloud optimized and general purpose systems actually experience the same challenges as that GPU optimized system that's doing 10 kilowatt? And next year even 20 kilowatt? What about the network equipment? What about storage? Are they all experiencing the same kind of challenges? This landscape is a lot more diverse than it used to be. And that means that we need to look at this landscape differently as well. We cannot just pursue that single solution. So before we can evaluate these kind of technologies, we're going to have to identify whether we're approaching this from, let's say, a chip manufacturer point of view or an end user. A chip manufacturer is aimed at the highest possible performance or thermal density of a chip of your highest product, and what it will be in a couple of years from now. That is a challenge you're solving as a chip manufacturer. But an end user is dealing with a lot more challenges, a lot more elements in that evaluation. And that all starts with the application. What does the application need? Because that turns into a set of compute requirements. And that turns into a selection of IT equipment, IT hardware, different types of hardware, storage, a combination of storage, networking, different platforms that facilitate that one application that you're running. Then you can mix in the facility environments, the facility requirements, or even the business goals. Are you just aiming for pure performance, or are you aiming for a highly sustainable environment? Certain sustainability goals. It makes a lot of difference whether you're trying to deploy an AI platform in Mumbai or in Canada, or whether you're aiming to roll out your cloud-optimized platform in India or in Singapore or in Northern Europe, and you would like to implement free air cooling. It really makes a lot of difference. So that means that we can ask this question, basically, can one size fit all these technologies? And the answer is no, it cannot. But there's a few things that we do know, and that is this. Over the next 5 years, every data center in the world will have to deal with liquid cooling in one way or another. It doesn't matter which, but you're going to be dealing with liquid cooling. Air cooling will not disappear. Absolutely not. A majority of the platforms will still be fine with air cooling. But we have to recognize that not a single technology will be or should be dominating the entire landscape. So what is it that we should do, or how do we move forward with this? Well, it really starts with setting up a unified liquid cooling infrastructure, an infrastructure that can facilitate all these technologies alike, whether we're talking about air cooling or liquid cooling. Honestly, that pipe outlet on a water pipe, on a water distribution system, shouldn't really care whether it's connected to an air handler or one of the in-row coolers that we're going to see here on the floor as well, or whether it's connected to a cold plate or an immersion system. For that pipe, that shouldn't matter. What really matters is that you can diversify your environment to your platform's needs. Because That's what's going to give you the flexibility that you're going to need across the industry. And as an industry, we, especially here within OCP, will have to focus on the interoperability of these technologies to make sure that these technologies can collaborate together, can jointly be deployed within the facilities. And that provides you with a multi-generational approach to cooling technology that future-proofs your facility. And it also puts you in a position where you and your customers can be completely technology agnostic. And this is a daunting exercise, of course. This is why Sandeep Ahuja from Intel, Tim Shedd from Dell, and John Gross from JM Gross Engineering, and myself have come together and decided to author a paper to help the industry make these kind of choices, to provide guidelines for this, to provide some advice on how to approach this. And obviously, this will be run through the cooling environment structure that we have in OCP. But for now, I just want to leave you with this. Brace for change. Please start engaging with the liquid cooling projects within Open Compute. Prepare for these liquid infrastructures in your facilities or with your technologies that you're developing, and start evaluating them. Get familiarized with all the pros and cons of every technology that's out there, and discover the power of combining them. Have you really thought yet about potentially putting a cold plate inside immersion? Have you thought of cascading thermal energy across multiple solutions? Try and figure out these values, and stay tuned for the new paper to help you with your needs. And for now, I want to say thank you, and I hope to see you all in the engineering tracks in the coming days. We're looking forward for a lot of excitement. Thank you.
Please welcome Google's Vice President and Engineering Fellow, Partha Ranganathan.
Hi, everyone. It's a pleasure to be here. It's good to see everybody in person. So much energy, and I see standing room only here, so really nice. So my talk is titled Sustainable, Secure Societal Infrastructure for the AI-Driven Era. And I'm going to structure my talk in 3 parts. I'm going to start off with talking about some of the opportunities we have ahead of us in terms of AI. I will present 3 minutes, security, sustainability, and scalability, and I'll talk about how we as a community can get together. And then I'll end with the call for action. Okay, so I don't think anybody's going to be surprised when I say that we are at a once-in-a-generation inflection point in computing. All the prior keynotes have talked about how we are at a very interesting point in terms of AI. But let's jump a little bit deeper into that. In prior talks, when I've given keynotes at Google, I've talked about how at Google, we work on the planet-scale computing that underlies all the services that power billions of users. And as part of doing that, we have solved some phenomenal challenges around how do we get high performance, how do we get efficiency, resiliency at hyperscale. But this talk, I'm going to focus on something different, AI. Now, our products have always had AI inside them, but what we have seen in the past year or so is a bunch of fundamental tectonic shifts, large language models, generative AI, that have supercharged all these projects. One of my very favorite examples is how generative AI is transforming productivity. If you look at last year alone, in Google Workspace, we had AI-driven writing and related optimizations used about 180 billion times. But it's not just the consumer part. If you look at enterprises, across different enterprises, whether it's technology, telco, media, retail, healthcare, finance, manufacturing, over and over again, we are seeing AI being used in a multitude of ways to be able to take complex data and make it intuitively accessible, to start providing more interactive natural language interactions for online interactions, and also start thinking about more creative content generation. And it's not just business alone. Generative AI has the potential to fundamentally alter everything that you can think about, whether it's health, creativity, entertainment, business, productivity, and so on. And of course, we have to do all of this while being very cognizant of our responsibility and ethics here. We need to think about safety, privacy, security, and so on. And so when you think about all of these advances in AI that we just talked about, they also have implications on our assumptions around the models and infrastructure that drives computing. In particular, this animation here shows the journey that we have taken at Google, starting all the way from the original transformer paper that underlies all the advances we see today to most recently what we announced at Google I/O, whether it's BARD or PaLM or the other models that we are working on. And one of the really interesting observations here is that we started off with models that had literally hundreds of millions of parameters, and we have evolved to models that are starting to be around trillions of parameters. That's about a factor of 2 every 3 months in the model size. And with great model size comes great compute. And so this picture on the right here shows how the need for computation has also been increasing at phenomenal exponential rates. And so really the takeaway here is that AI is not only a powerful enabler, but it's also a fundamental platform shift. And we as a community, we need to innovate across hardware and software to think about how we are going to provide the infrastructure that drives this AI-driven future. So this leads us to a bunch of very fundamental questions that we need to answer. How do we design scalable hardware and software platforms to provide these ML supercomputers that drive AI? How do we deliver these systems with incredibly high amounts of reliability, safety, availability? And third, how do we optimize for these systems, delivering these at extremely high levels of efficiency, the greenest possible system across all of these broad industry ecosystems? In short, how do we design sustainable, secure, societal infrastructure for the AI-driven future? So I'm going to talk about each of these very briefly. So let's start with sustainability first. Now, when we think about sustainability, we all realize it's an absolutely important imperative that we care about. Google in particular is really passionate about this space. We have made some very audacious goals, whether it is 24/7 carbon-free energy by 2030, or whether we talk about net zero carbon, not just across our operations, but also across our value chain by 2030. And so how do we kind of, as an industry, get together to address some of these audacious goals? So today, I'm very, very happy to announce the Net Zero Innovation Hub for data centers. And interestingly enough, this started off as a proposal in OCP's Regional Summit earlier last year. And we've been just blown away by the response that we got for that call. And so together with Microsoft, another Open Compute member, and Danfoss and Schneider Electric, we are very, very pleased to have the first pan-European public and private collaboration to address sustainability at a regional level. And we think this model has the potential to expand to other regions and geographies as well. And I'm very pleased, again, at the momentum that we already have with the Innovation Hub. We already have a lot of really good conversations, and we are also starting to see some specific work streams emerging around waste heat and grid availability and so on. I also want to highlight 2 other very interesting contributions in recent times. The first one is around greener concrete. Across all the hyperscalers, Amazon, Microsoft, Meta, and of course Google, we got together and we put out a very ambitious industry roadmap to decarbonize concrete in the data center. Now, concrete in the data center as a fraction of the total carbon footprint in the world is not significant, but concrete across all industries is more than about 10% of the total carbon footprint. And so our hope is that this community, our industry together, we can set the standards for some very ambitious goals in concrete that elevate the entire industry together, entire world together in terms of some of our concrete stuff. And so I'm very excited about that. The second thing we want to talk about here is what Google has been doing with others on the DCF sustainability workstream. And in fact, I think we are addressing what is probably the most fundamental problem in sustainability, namely the availability of clear, consistent, standardized metrics. And these are not just metrics for emissions and carbon, but also energy, water, circularity, ecosystem as well. So that was sustainability. So now around security, I want to talk a little bit not just about security in terms of confidential computing, but more broadly in terms of reliable computing as well. And so the first thing I want to talk about is our contributions around Calyptra. So how many people here have heard of Calyptra before? Okay, a good chunk. So we announced Calyptra last year along with our founding partners, Microsoft, AMD, and NVIDIA. And today we are very happy that compared to the draft spec that we had, we now have IP ready for root of trust in CPUs, but also in GPUs and all possible SoCs. And our membership has expanded to a large number of companies as well. Similarly, I'm very excited that today we announced OCP SAFE. SAFE stands for Security Appraisal Framework and Enablement. And what we have done is we have taken a lot of the best practices that we have at Google and other OCP member companies, and we have provided a standardized approach to look at everything across the server lifecycle, provenance, code quality, supply software chain, and look at multi-vendor agnosticity in terms of how we do that. In reliable computing, I've talked in the past about the problems with silent data corruption, and so I'm very happy that we now have open SDC frameworks. But we've also been thinking in terms of specifications and standards around server component resilience and testing that we have contributed as well. And finally, I'm very, very happy that for the first time in Open Compute, we now have this new OCP academic program where Google and other members, we have 4 other members now and more joining, we have gotten together to produce an academic corpus where we can encourage future innovation, future research on this very, very important problem. So I'm very, very excited to see how this experiment goes. The third part is around scalability, and this is something, again, that we do really well at Open Compute. And scalability is not just across compute, but it's across compute, storage, networking, all the way from silicon to cloud. And here I really want to call out a whole bunch of contributions that we have been making around infrastructure for AI ML. So it starts off with everything from the base silicon accelerators, things like chip-level specifications for 8-bit floating point. But we've also been looking at RAS specifications for firmware and how do we build accelerator systems. And then my all-time favorite, how do we think about OpenXLA or compiler infrastructure to encourage the innovation that we want to see across hardware and software. Again, in the spirit of the industry-academia collaboration that I talked about earlier, we also have an announcement around Architecture 2.0. And this particular effort is really interesting to me because beyond just the traces and the data sets and the tools and infrastructure that we are looking at, we are also thinking about going beyond just systems for AI to thinking about AI for systems. And I'm very excited to see where that goes as well. And then on networking, today, Google announced that we are opening up Falcon. So Falcon is our very reliable, low latency, high performance hardware transport protocol, which has decades of Google innovations in this space. And we are opening this up to Open Compute and all the Open Compute members. And we see this as part of the broader efforts to advance Ethernet as a high performance networking fabric, both for hyperscale and for AI ML workloads. And you heard Ram talk about this a little bit earlier as well. And then on storage, we continue to make a whole bunch of contributions, particularly around NVMe for fault tolerance. So we are looking at key management, but we are also looking at flexible data placement and various aspects with NVMe as well. So that was kind of a quick whirlwind tour of the various contributions we've been making around some of the most fundamental challenges, sustainability, security, scalability, as we think about the AI-driven era. But really, this new era of AI systems is going to be underpinned by a healthy, open industry ecosystem. And so Google, of course, we love open source, whether it is something like Kubernetes or TensorFlow or JAX or Chrome or Kaggle. We've always kind of believed in the value of not just open standards, but also building healthy ecosystems and being able to share best practices. This summit is a great example of something like that. And our partnership with Open Compute has gone for multiple years, all the way starting from when we first contributed our 48-volt power supplies to today, where we are engaged in a whole bunch of activities, including Amber Huffman, who's on the board of directors, and we are engaged in all the work streams there. And in this summit alone, we have more than 30 different talks from Google. So I'd encourage you to go there and really cheer everyone up as well. Lots of really nice contributions there. So all of this open industry ecosystem cannot be possible unless you have a healthy spirit of collaboration and co-design. And so that is kind of my call to action here. And hopefully you've seen this in the talk throughout. It is not just collaboration across multiple companies in Open Compute. It is collaboration and co-design across hardware and software. It is co-design across compute, network, storage, and infrastructure. It is collaboration across industry and academia. It is collaboration with startups. And so I want to leave with that as my last concluding point. It is not often that we as a community get to be on the ground floor of a step change in computing, a fundamental, pivotal, tectonic shift in computing. We are at that moment today. The AI-driven era is going to fundamentally alter how we think of computing, and it's going to fundamentally alter how we think about designing hardware and software systems for this new era of computing. And so this innovation, whether it's around security, sustainability, scalability, is really going to build the fundamental societal infrastructure for the future. And we can only do all of that together. And so hopefully, as you're listening to all the other talks in the summit in the next 2 days, I'd invite you all to join Google and Open Compute. And I'm really looking forward to seeing what other advances come up in the future. So thank you for your time.
Please welcome Microsoft's Corporate Vice President, Silicon, Cloud Hardware, and Infrastructure Engineering, Reynold Desa.
Good morning, everyone. I hope you're enjoying the summit so far. It's a pleasure to be here at the OCP Summit. Before I jump in, I want to talk a little bit about Microsoft's partnership with OCP and why we're so passionate about the OCP community. Microsoft joined OCP in 2014. And since then, we've made over 50 contributions, all the way from rack design to server architecture, along the lines of security, liquid immersion, and more. And like today, collaborated with OCP Safe contribution. We're also proud to have Microsoft represented on the OCP board. Zaid Kahn, who kicked off earlier today, he's on the OCP board as the chair. And we've got a couple of members on the steering committee too, very actively contributing to the OCP community. When it comes to building the Microsoft Cloud, our work to standardize designs for systems, boards, racks, and other parts of our data center infrastructure is paramount to increasing the pace of innovation across the computing industry. We've experienced firsthand that working with the open compute ecosystem, we can achieve standardization, consistency, and interoperability, which are benefits that we pass on to our Microsoft customers. We have consistently tapped into the power of this OCP community to address common issues, working together to identify and ideate across the needs of the future, which today is a lot of conversation around AI. So the buzz around AI is hard to miss these days. I believe that AI has the potential to be one of the biggest disruptor, more so than the invention of the internet, and it's going to be more prevalent than ever. A recent study found that more than 75% of leaders believe AI will give their organizations a competitive edge. So now they're all asking the question, how can my company seize the full advantage of AI? With Microsoft Cloud, we help our customers power their AI transformation in 3 big ways. First is we built AI capabilities into the Microsoft Cloud solutions that our customers are already using today. We're helping them to be more productive, more creative, more efficient, and more innovative. This is what we mean when we talk about a co-pilot for every Microsoft Cloud experience. The second thing is we're making it easy for any organization to co-innovate with our partner ecosystem and build their own intelligent apps and co-pilot solutions using the same stack and AI services that we ourselves use. And third is we're doing this all on a foundation of trust. Every organization needs to safeguard their businesses, their customers, and their data, particularly in the era of AI where we're all still learning. The Microsoft Cloud runs on trust, and we're helping every organization build safety and responsibility into their AI journey from the very beginning. Okay, so now let's take a look at the shift and how it's transforming our approach to how we are building the hardware infrastructure. Okay, so here's kind of the problem statement. For decades, our industry has worked to achieve incremental progress on performance per core, performance per watt, memory and storage bandwidths, networking, and we've been eking out gen over gen improvements thanks to the goodness of Moore's law and everybody's creativity here. However, the rise of generative AI changes all of that. The speed at which AI models evolve is outpacing our current innovation, and how quickly we can evolve the supercomputing architecture and hardware is going to be key to meet this new challenge. This is a very difficult problem to solve. The graph you see behind me kind of illustrates the scope of the challenge. And there are many similar graphs you can show that represent this. The large line shows the growth in computational demand for successive generations of the large language models. And by one estimate, that's growing at about 750x every 2 years. And you can kind of look at the bottom two lines there, the yellow and the green line, where that improvement on the memory and the storage is growing at about, and the network is growing about 2x every 2 years. So there are very similar challenges, and you can draw graphs like this with respect to power delivery, cooling, and many other dimensions. Okay, so with that as the problem statement, we are at an inflection point. And as engineers, this is a problem we must step up to solve. We need to continue to meet the ever-growing exponential demands of the AI users, while addressing critical challenges in the hardware infrastructure around cooling, around the energy wall, and then also doing this in a very sustainable way. To solve these challenges and meet the reality of AI, we must look for opportunities to innovate what I call across the hardware stack, because there's optimization points in each of these domains, as well as optimization points across the stack. And then we've also got to look at it across the life cycle of the development, because we got to look at it from how the energy is used, how we are developing it, as well as how we are decommissioning from a sustainable kind of way. This is where the greatest potential lies, and we have a role to play, and we all have a role to play. OCP is a highly independent ecosystem, from chip designers to foundries to system companies like Microsoft. And it's a collaborative strength of this community that will help set industry standards and with that, accelerate the pace of innovation. Although the problem, or should I say the challenge, is large, the opportunity and potential is much more. As a community, we need to address these collaboratively and set standards where it makes sense. So with that, as I mentioned earlier, designing for AI requires massive computational power. It requires powerful GPUs, new types of processors and accelerators with novel architectures that deliver cutting-edge performance with high-density packaging and in a small physical footprint. And to manage these massive training data sets, we'll also need to rely on advanced packaging technology and the use of high memory bandwidth. And as I said again, we're going to have to do all of this while taking into consideration thermals and power efficiency. And since AI supercomputers are essentially also distributed systems, we also require scalable networking infrastructure to seamlessly accommodate these logical clusters of a large number of thousands of processors that are spread across sometimes data centers. This is really pushing the boundaries of scalability to unprecedented levels. And if you draw the line out, it exponentially grows. So we have made great strides. In this. The whole industry has done some creative innovations. We've moved from monolithic to chiplet-based SoCs, and we continue to see the power and performance gains in each generation. Now we are faced with the opportunity to drastically shift how our hardware infrastructure can fuel the world's appetite for AI. And as an ecosystem, we have an exciting opportunity. We're kind of on the ground floor to establish the standards on which the hardware infrastructure will be developed. So one of the things, the theme of this year's OCP Summit is scaling innovation through collaboration. And I'm very thrilled to announce the first contribution here, which is microscaling formats, or otherwise known as MX. Data types for AI are evolving rapidly and are a major driver for future AI hardware capabilities. Microsoft has been investing in hardware, software, data science IP, and know-how for AI training and inferencing for many years. Earlier this year, we drove the formation of an MX Alliance to come together to make advancements in this space. In partnership with AMD, ARM, Intel, Meta, NVIDIA, and Qualcomm, we've standardized a fine-grained scaling method for narrow bit data formats that will be used for training and inference AI applications. And this is known as microscaling. Before highlighting the why MX is important, I want to point out that the best things about this specification is that it was created with users in mind. MX was designed to reduce the user friction, and in some cases even serve as a drop-in replacement to already existing industry formats. Now let me talk about the benefits of MX. The MX-compliant formats basically enable efficient AI computation in a given clock cycle. So what this does is your inference times and your training times reduce, which again is a benefit for the customer. And in addition, it also drives sustainability, because now the amount of compute we're doing, the amount of AI computations we're doing requires uses much more efficient compute, which again helps with our sustainability, sustainability goals. As we push into this ecosystem with our partners, we're confident these advancements and standardization efforts will continue to further propel innovation. So we're incredibly excited to work with key industry leaders across the system and drive the unified standards in AI data formats. For those that want to take advantage of these benefits or learn more, the spec and an academic paper which provides more details will be released through OCP and is also available on the blog. I'm also very excited to announce the next contribution, which is GPU and accelerator management standardization. The increase of generative AI has led to a diversity of GPUs and accelerators from various suppliers, as well as the pace at which it's come out generation over generation has grown. But what this has actually done without standards is kind of led to like bespoke models of how you manage these accelerators or GPUs in our AI hardware infrastructure. So this basically is a burden for the hyperscalers, as well as these GPU suppliers, as you kind of work together with each and every new rev or new generation or new supplier. To address this challenge, thrilled to announce our contribution with NVIDIA, Google, AMD, and Meta on the creation of GPU and accelerator management standardization. And this will help keep up with the exponential needs of AI. This initiative features standardized protocols and interfaces, enabling designs that are agnostic to the hyperscalers through standardization. There are a few work streams that I want to talk about with respect to this contribution that has driven this. One is a standard-based approach to how we update firmware for the GPUs and the accelerators in the hyperscalers. Second is standardizing RAS requirements for GPUs and accelerators in hyperscale computing. And third is around interfaces. We've accelerated the deployment of GPU-based systems using DMTF industry standards. The benefits are immense, and we predict significant time-to-market improvements for onboarding new accelerators and GPUs, which eventually accelerates the pace at which we can provide AI solutions to our customers. Through OCP, this contribution enables not just a spec, but a method to even enforce these standards with the GPU and the accelerators, and they are not hyperscale specific. Finally, through the lens of scaling AI, this initiative is also a springboard for us as a community to define more areas where we can commonly standardize and scale rapidly. Okay, so I'll leave you today with a call to action. As I said, we are on the ground floor of the AI hardware infrastructure, and there's a lot of room for standardization. We've made tremendous progress, but we know where we are at now is not enough. The challenges of memory and networking, as I mentioned earlier, are just the beginning. And so we've got several opportunities where we can collaborate together as a community to further accelerate and drive growth. I kind of put my three areas here. The first is the power or the energy wall. As the demand for AI grows exponentially, the need for power also goes up. And we've got to be very creative and innovative to try to address the challenge, because we cannot continue to increase the use of power without any constraints there. So we have to innovate in this space. The other is around modularity. We need to standardize and reuse wherever we can. I shared some of the areas of standardization where we can make a lot of our building blocks modular, again, giving more value to our customers at the end of the day. And last but not least is sustainability. With areas, we got to take care of our carbon footprint as we build the AI hardware infrastructure to meet the needs of the AI growth. Through this OCP community, we have an incredible opportunity to enable the transformative power of AI throughout the hardware stack and across the industry. So looking forward to partner with everybody to explore new frontiers. And with that, I want to say thank you, everybody, for your time, and I look forward to the continued partnership through OCP.
Please welcome Meta's Vice President, Data Center Infrastructure, Dan Rabinovitz.
Good morning, everybody. I'm Dan Rabinovitz, and I do hardware stuff at Meta. And I'm going to talk to you about what's happening with Gen AI and all of the challenges it imposes on us on the infrastructure level. So one of the things that's really interesting right now is you might have thought that Gen AI was kind of in its hype cycle. But what we're seeing with the emergence of Gen AI now integrated into messaging apps, into consumer electronics devices, is that the number of actual inferences are starting to grow at a very, very fast clip. And these are useful things that are now enabled so fantastically well by the fact that we've trained these large language models and they've become quite productive. And the next generation are going to combine machine learning with Gen AI, extended reality, so that you can actually get really cool use cases like real-time language translation, looking through your glasses to tell you what something is, or what is that leak thing and what do I do about it? These kinds of use cases are going to drive way more inference transactions on our infrastructure, which just means that Gen AI is on a roll right now, and we should just expect this tsunami to continue. But just a very short time ago, in 2022, which is, as many of my colleagues have said, less than a year ago, we were focused on deep learning recommendation models, which are really the models for our company that tie people to the content they love. And we were optimizing these things around memory and I/O bandwidth largely. We weren't really compute intensive in the same way as Gen AI. Fast forward just a very short time later, Llama was trained with 65 billion parameters, 400 times the amount of flops required. We needed 10 times the memory capacity. And as you can see, now we're not talking about like one GPU, but we're talking about 20 times the amount of GPUs to do these kinds of training jobs. So pretty dramatic change. And we're not done. We actually don't know where diminishing returns are for generative AI models and large language models. So this is just more to come. And I think we should expect that we're going to continue to get challenged on the scale and the complexity and the evolution of these models. And the models themselves will change. So we really need to expect the unexpected here. The only thing we can look at right now is all of this complexity is posing a gigantic challenge for us in the industry. So we could have made this a much more granular picture, but these are 5 dimensions that are reasonably well taxed by different kinds of AI workloads. And I want to talk about this in the context of generative AI, large language models, and ranking and recommendation for inference and training, so that you can kind of get a visual for what are the most taxed dimensions as we look at these different kinds of models. So if we look at large language models, these are trained with billions and trillions of parameters. They require a huge amount of scatter and gather transactions. And that's needed across thousands of GPUs to get sufficient flops to process these jobs. And if you look at this, super duper compute intensive, lots of network bandwidth required. The inference phase for LLMs is split into 2 phases, prefill and decode. And the prefill phase is very compute and memory intensive, requiring up to 10 petaflops just to get to that first token. And And think about this in the context of what we just watched. Because now we also have to think about the decode phase is very sensitive to latency, to network latency and memory bandwidth, because those tokens are processed one at a time. So you want things to come in as fast as possible so that when you're asking your chat message bot what to do, you don't have a long lag. You get really good response time. Now, switching over to ranking and recommendation, if you look at DLRMs, they have large embedding models that are mapped across machines, many, many machines, and that results in a high demand for network bandwidth because we have a lot of all-to-all collectives that are being instantiated in these particular kinds of models. So you can see, very sensitive to network bandwidth. On the inference side, and this is really interesting, so if you think about this from, and we'll just put it in the context of our business, we have a lot of this kind of workload. This is a very high demand, high transaction workload for us. So we've been tuning these models to make sure that although they require a lot of memory capacity, we try to minimize the amount of compute bandwidth that's required or the compute capacity. And with all of that tuning and training, this is kind of what these models are really taxing in the data center today. Now, if we overlay all of these, you can very quickly see, man, we are like very, very far from having a system solution that could work for all of these different kinds of workloads. It's pretty dramatic. You pick like 4 general categories and you end up with this, which is fairly messy. And keeping this in mind, it's really, really important for us to now accept the fact, and I think some of our colleagues said this earlier today, it's hard to find one thing to rule them all. And more importantly, coming back to the earlier point, models and parallelism are going to continue to evolve and change. So we don't actually know what will be the look and feel of these models going forward. Now, I'm a two-wheeled enthusiast. I can actually describe this as sort of a disease. I have a lot of bikes. And it's the same problem, right? Some people will say, well, why don't you just have one bike? And I could say, a gravel bike can go on the road, it can go off-road, but it's never going to be as fast as a road bike on the road, and it's never going to go down those gnarly single tracks as well as a full suspension mountain bike. There's trade-offs. Performance per watt is actually a shared metric between cyclists and AI systems engineers. We care about that stuff. And we try to optimize and tune these solutions for the application that we're going after. So it's pretty normal, actually, to try to optimize and get the best performance for the highest volume workload that you're going after in AI. Just like in cycling, you definitely don't want to be riding your mountain bike in a road race because you will lose to all of the road riders. So where does that take us? This, I think, is kind of like the big question for OCP right now. Because if you look at this landscape, how on earth do you take this particular situation that we're in right now, especially when you consider that a lot of companies are developing their own silicon, vertically integrating as much as possible, and finely tuning the systems to suit their needs? How do we go from that reality to open and letting lots of companies come into this ecosystem and deliver value so that we don't have to make all of these bespoke solutions? I think the answer is starting to emerge. So the open model is already out there to some extent. And we see this most obviously in areas like software frameworks. So PyTorch, Llama 2 being an open model that anybody can use without having to spend the money or the energy to go train models by themselves. These are like good first examples of things that are starting to take off. They have scale, and anybody can basically come in and adopt these technologies, and they're being supported by a community, which is really critically important. But if you look at the hardware situation, it's not quite there yet. And today, I would like to encourage all of us to think about a renaissance, a rebirth of this mission around OCP called OCP 2.0, with a really strong focus on unlocking this challenge in AI. Now, our AI journey began with Grand Teton, and I'm very pleased to announce that we've contributed this design to OCP. and you can have a look at it. It's available at the booth. And importantly, we are eating this dog food ourselves. Grand Teton clusters are in production volumes, running in our data centers for both inference and training. And as much as I would like to celebrate this and say this is awesome, and by the way, this is your design, so this is an OCP design, anybody has access to it. It is cool, but honestly, we're still in diapers. Like this is like toddler time in terms of where we need to go next. And I just want to acknowledge that we are at the beginning of a journey and we are only 1% done. So what does this look like from a homework perspective? So if we were taking OCP 2.0 seriously, and I'm really lucky to be going in this particular speaker slot because so many of my peers and colleagues have been able to already tell a big chunk of this story. But we really need to start with common rack and chassis architectures. And what's cool is, just like we talked about with bikes, we don't need air cooling for every workload. We're going to need liquid cooling for some of them, but some of them we do want air cooling. Some of these, we want to be able to depopulate some of the network bandwidth capability when it's not required. In others, we want to have it fully populated. So starting to think about common chassis and rack architectures that can support all of these different configurations is important, because if every single rack and chassis is completely different, it's really hard to scale. So we'll have to accept some compromise on cost, et cetera. But I think leaning towards this goal of commonality is really important. A lot of folks have talked about liquid cooling. Liquid cooling is here. We cannot avoid it. It is important, but it is still very early in its life cycle. And we have so many things to work on around cold plate reliability, how we ship things in production, how do we do leak detection, how do we standardize field replaceable CDUs? All of these are kind of open questions. Even just the kind of hardware you use for blind make connectors, that's not really been standardized, nor do we have enough qualified vendors who have really robust solutions that we can go to mass production with. This is definitely number 2 on the list, and very closely related to what we talked about with the common chassis and rack architectures. The next thing, and I will just say, we learned a lot going through the Grand Teton exercise about how hard it is to integrate, validate, and test large AI systems, particularly at the cluster level. Even at the rack level, we found very significant variations in yield when we were not actually testing the subassemblies and the racks by themselves sufficiently so that we could actually continue to improve yields in manufacturing. And all of our manufacturing partners are going to struggle with this as they get started because the systems are way more complicated, things are more finicky, and we have to spend more time on this particular area. And this knowledge is not that useful if it's only with 2 or 3 companies. It actually needs to be shared more broadly so that the entire industry can actually come up faster to be able to support these in mass production. The next thing to think about is universal tooling and telemetry and software. I was really happy to see all of the work around GPU telemetry being standardized, understanding and identifying and isolating silent data corruption in the field. There's a whole range of things that are going to be really important here, not least of which is when we start to look at 32,000 and beyond GPU cluster sizes, we have to have good telemetry to determine what's stopping a job running reliably. And it could be any of 100 or 1,000 things. But without any commonality around that telemetry, we will continue to reinvent all of the reliability engineering that maybe 1 or 2 companies will figure out 1 or 2 years earlier. That's actually not really helping in terms of getting to scale. And finally, as many of my peers have talked about, we need a unified back-end fabric. And I'm really excited to see that Google announced Falcon today, and Ram was talking about UEC. We applaud these efforts, and we really believe that the industry needs this standard because this is actually very critical to the future of AI performance. All of this requires sustainability. My colleagues have talked about this in detail. It's incredibly important that we address those upcoming power and cooling needs. So what I want you to take away is AI infrastructure is here, it's growing, it's getting more complex, and we don't know where it's going. OCP 2.0 is a rallying cry for all of us to step up to the plate and start to address these issues as a community. And by the way, we need a community to do this because no one company can do this alone. So thank you so much, and I look forward to seeing you all in the house.
Please welcome OCP's Director of Global Events, Kaylee Burdett.
Hello, everyone. I promise I'll let you go get some lunch soon, but I just wanted to take a moment to review the schedule with you so that we can make sure this summit is productive, informational, easy to navigate, really just a great overall event for each and every one of you. Now that keynotes are over, the expo hall is open. We have over 70 booths packed with the latest OCP gear, so I encourage you to go visit all of our sponsors. We also have the biggest experience center ever with 55 companies collaborating to bring you live demos. This afternoon, we also have our always popular executive sessions and our AI special focus track. And I hope you'll join us this evening for our welcome reception in the expo hall, where we'll have drinks and hors d'oeuvres. All day tomorrow and Thursday are our breakout sessions, which are the in-depth technology discussions from our OCP project groups. We also have our more special focus tracks like optics, quantum, and deployments. We have 17 tracks. That's a lot, I know. But don't worry if you missed something. All of our sessions are recorded and will be posted to the OCP website in the weeks following Summit. Also tomorrow is our Future Technologies Symposium, so you can see the posters and presentations from the selected authors, as well as our technology demonstrations, which is new this year. Tomorrow afternoon is the Hackathon Awards and presentations and our Symposium Awards, so please join us there in the Expo Hall for those. And then we'll head outside in front of the Convention Center for the OCP Block Party. Our event wraps up on Thursday with more breakout sessions and, of course, all of the activities going on in the Expo Hall. We ask that you wear your badge at all times, and if you check behind it, tucked inside is an insert that has a QR code. If you scan that, it'll bring up the full schedule, where you can sort and filter by track, day, speaker, and more. The insert also has a full map of the summit, as well as the Expo Hall floor plan and other helpful information. If you have any questions during the event, I encourage you to stop by registration, or you can find an OCP staffer. We'd be more than happy to help you. This event would not be possible without the support of our sponsors, members, partners, volunteers, and the OCP community at large. So we truly appreciate each and every one of you being here with us this week. And on behalf of the OCP Foundation, we thank you and we welcome you. Let's have a great summit.